Hello, it's Mr. Pfeiffer here, and today we'll be talking about momentum and collisions. So first, let's go ahead and define what momentum is. When Newton wrote about momentum, he said that it was a change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed. So let's try to put that into English. This change in motion he's talking about here is this change in momentum, which we'll define in a minute, and it's in this direction of the force. So it takes a force to get a change in motion. We saw that in Newton's second law, and actually the second law and momentum are very closely intertwined, and we'll see that later. So here is our definition of momentum. Why they use P, I have no idea, but P is momentum, and that little symbol over it just means that it's a vector. If you recall, we've looked at some vector quantities before where momentum was vectors were things like speed versus velocity and distance versus displacement. So if it has a magnitude and a direction, so magnitude is how big, and then the direction is obviously which direction it's going, then we call that a vector. And then so we have mass times velocity. So notice things that are made up of vectors are vectors. Let me get that. Okay. Now, what are the units on momentum? Well, mass is measured in kilograms, so we have kilograms. Velocity is measured in meters per second, so kilograms times meters per second. So we would just say kilogram meter per second. Now, this total momentum is a vector sum. This gets more complicated as we go into 2 dimensions, but we're only going to stay into 1 dimension in this class. So it's kind of looks like this. If we have 1 in the positive direction and 1 in the negative direction, let's go ahead and calculate what those momentums would be. So take a minute and try to apply the equation for these 2 masses. Pause it now. Okay, so here we would say that the momentum 1 equals the mass, 3 kilograms, times the velocity, which is 10 meters per second. And that would give us 30 kilogram meter per second. Yeah, that's a K. All right, now we go over here to the same thing for momentum 2 would equal 3 kilograms still times. Now it's in the negative direction, so I'm actually going to use negative 5 meters per second. And that would be negative 15 kilogram meters per second. So if someone asked what was the total momentum of this system of looks like 2 masses, you would have P total equals 30 minus 15 positive 15 meters per second. Now, you don't have to include the positive, but I like to do that, especially when we're talking about vectors, because it lets people know that, oh, that's in that direction. So, all right. Now, let's talk about changes in momentum. So whenever we talk about collisions or things acting, either one object acting against a wall or 2 objects acting with one another, we're going to have a change in momentum. Now, we can do that by a couple of ways. one of them is that we'll write it as delta P is P final minus P initial. So let's go ahead and just keep going along here. P final, okay, what is the mass? Okay, a ball heads into a wall at 10 meters per second and bounces straight back at 7 meters per second. Its mass is 2 kilograms. Find the change in momentum. Okay, well, in the end, the mass of the ball was still 2 kilograms times. Now, we're saying back at 7 meters per second, so I would use a negative 7 meters per second. That's my final, minus my initial, which would be 2 kilograms, times initial, which was 10, so we get negative 14 minus 20, so negative 34. Then what are my units? Kilogram, meter, per second. Now, sometimes we'll write change in momentum a little differently, but it really is the same thing. Sometimes we'll write it like this. Change in momentum is m delta v. Well, why do we do that? Because the mass of the object didn't change, and if we look at our example above, we really could have factored out that too. So let's just do the math and see if we get the same answer. So here we have 2 kilograms times the change in velocity, which would be final velocity, negative 7, minus your initial velocity of 10, and that equals, unit should be in there, 2 times negative 17 is still negative 34. All right, so this will come into play a little bit later because we're going to see it in this form, m delta v, in a little bit. So, most of the classes have seen the video of the egg going into the wall and into the bed sheet. Hopefully we had a chance to actually try that out, depending on how supplies worked out. So let's take a minute and just discuss why this happens. If you did not, I'll go ahead and just quickly show this clip. You did, you can fast forward the...
Here's my favorite demonstration of impulse. I have 2 eggs, same mass. I'm going to try to throw each egg with the same velocity. That means they have the same momentum. If the impulses were equal, why do we have such dramatically different results? The wall applies a big stopping force over a short time. The sheet applies a smaller stopping force over a longer time period. My students say the sheet has more give to it. Both stop the egg, both decelerate the egg's momentum to 0, but it takes a smaller force to reduce the egg's momentum over a longer time. In fact, so much smaller that it doesn't even crack the egg shell. Now let's relate this to...
Okay. Let's go ahead and move that. So let's crunch some numbers and variables and take a quick look at what we know here. Newton's second law says F equals ma. We're all okay with that, I think. Acceleration is velocity over change in time. Now, instead of writing triangle V, that's a delta, we know that that's change in velocity. So that's my final velocity minus my initial velocity. Mass can distribute over mass times velocity there, mass times velocity there, and you end up with mv final minus mv initial. Well, where did we see that before? mv final minus mv initial. We've actually already done that calculation. So we keep that we haven't broken any rules of math yet. We just have mv final minus mv initial on the numerator, the top, and change in time on the bottom. We can rewrite this as force equals change in momentum divided by time, change in time. And I would even take it a step further over here to get it into a more usable equation for us when we're solving impulse and momentum theorem problems. So here I would write F equals delta P over delta T. Multiply both sides by delta T. This cancels, that cancels. So we get change in momentum equals time, change in time times force. Most people will write that like this. Force times change in time. Yesterday we covered about how force times change in time was what we defined as impulse. Right? That's our definition of impulse. A force acting on an object over a period of time. Now, change in momentum. I'm actually going to write that using one of the ways that we used earlier. I'm going to write that as mass times the change in velocity. And this is something that I would say is the equation that you really want to focus on for the homework. Oops. So, magic pen. Yeah, there we go. So, moving on. Force times change in time, impulse, equals... that's not very good. I'm going to fix that. Equals mass times change in velocity. So, if we have something that's quickly changing its momentum, in other words, it's gaining a lot of velocity, what will often happen is we have a lot of force exerted over a little bit of time, like something like a punter kicking a ball. If you're in a car collision, you'll see this change in time value is pretty small. Obviously, if we wanted to maximize the change in momentum over here, we would try to exert a large force over a large amount of time. So take a minute, brainstorm some ideas of where have you seen situations where this might apply. So pause it now. All right. So here we have an actual numeric problem that has the impulse momentum theorem in it. So a ball heads into a wall at 10 meters per second and bounces straight back at 7 meters per second. If its mass is 2 kilograms, find the change in momentum. Then it says, if the change in time is this, find the average force. So I'm going to jump straight to the equation that we had before. Let me get my pen out. F delta T equals M delta V. Delta V. Force is what we want to know. So solve this. Take a second. Solve this for force. So without using any numbers, we can just use our algebra. We should be good to go. Divide both sides by t, and you get force equals mass times velocity final. This is delta v. I'm just rewriting it. Times minus velocity initial divided by, well, delta t is just given as delta t. It would be final time minus initial time, but they give it to you as delta t. So let's plug in our numbers. Now this one I'm not going to worry about labeling all the units in each step, because if I'm looking for force and I put all standard units inside of here, I'm going to get standard units out for my force. And hopefully you know that the standard units of force are newtons. So let's go ahead and start this. What is my mass? 2 kilograms times velocity final, -7, minus velocity initial, 10. I said -7 and wrote -2. Oops. -7 minus 10. Then we divide it by your change in time, 0.02, and you get we end up with -1,700 newtons. I know it's newtons because everything that I plugged into here was scientific units. So that's where we're going to stop for today. Hopefully this got you thinking in the right direction, and I want you to now work on the worksheet that has the answers on the bottom of it, so that way you kind of know if you're on the right track. Show your work, obviously. If the answers are given, we're grading the work. And then that's your in-class work. And for tonight's homework, you have another worksheet that will be gone over. We'll go over it tomorrow. So thanks for watching, and I hope you guys pick something out from this. Thanks.